So my two x-intercepts written as points are what? -2, 0, -6, 0. What's still left to get here? I did part D. The y-intercept, and I should only have one, but I'm guaranteed to have one. So the y-intercept, this is part E. We do f of 0. Now you must be careful when you do f of 0 in standard form, because it doesn't work as nice as it did in the other form. So negative, wait, was it negative? Yeah, -5. Replacing x with 0, 0, plus 4, squared, plus 20. Was that it? Sorry, okay. So I replace the x here with 0. What do you get there? See, this is 4 squared is 16. What's 16 times -5? -80. All right. 16. What's 16 times 10? 16 times 10. And then 6 times 10. Or, how do you do that in your head? Does anyone have a way of doing 16 times 5 in their head? 6 times 5, 30. And then 10 times 5, it's 50. 50. Negative 80, whatever. All right. -80 plus 20, is that it?
Yes.
That's what, -60? Ooh, that's way down my y-axis, right? That's going to be at 0, -60. All right, so let's draw this. And I'm going to do something a little different on this one, which is completely legal. It's allowed. It's very helpful when you're trying to draw something. Now first, notice that I'm really only focusing on the left side of the graph. That's because I know my vertex is what? -4 and up what? What was it? 20. So, and down, I have to be able to go all the way to -60, don't I? What about left and right? I only need to go to -6. So this time, instead of doing like 5, 5, 5 each way, I'm going to change the scale. I'm going to say, this is, let's say, 2, 4, 6, 8, 10, so -10. So each of these are 2. But in this direction, I'm going to count each of these as 10s. 10, 20, 30, 40, 50, 10, 20, 30, 40, 50, 60. Understand? You could count by 20s. The point is that you are allowed to change the scale, the difference between the x and the y-axis, but you cannot change within the same axis. So I can't go, this is 10, 20, 30, 40, and then here say this is -20, -40. Understand? Up and down, that's 10, 10, 10 each one. I can't say then below it's 20, 20, 20. Can't do that. So the same axis has to stay the same the whole time. That make sense? Okay, so let's plot our vertex, which was -4, +20. Let's plot our x-intercepts, which were at -6 and -2. And my y-intercept, which was way down here at 0, -60. And then I draw myself my parabola. Axis of symmetry. That. You don't have to put it there, but sometimes it helps in graphing. You can do something like that. And then I've got to get down here to this point like this. So the way that I use the axis of symmetry is like this. If I move down to my y-intercept, see that distance right here? it has to be the same distance on the other side. So I could mirror a point over here to help guide me in drawing this side. All right, that's it. Do we understand? Everyone clear? Two different forms of quadratic functions, how you would graph them in either case. All right, now we'll do an application, which means we'll talk about one particular usage of a quadratic function in the real world. Falling objects on Earth. I like to give this little demonstration. Okay, it's going to be loud. Book, paper, right? We'll let them go. You ready? Okay, so the book hits the ground first. Why? Because it's heavier? Heavier than the paper. Do we agree? Show of hands. Heavier? Paper? What do you think? Heavier? All right, so if it's heavier, if you think the book's going to fall faster than the paper because it's heavier, then what should happen if I put the paper on top of the book?
It should fall the same way.
Why would they fall the same?
Because you have no air pushing between the
But, okay, yes, but if I'm saying, though, if this is falling faster because it's heavier, then shouldn't it fall away from the paper? I'm saying if your argument is that it's falling because it's heavier, then this should fall away from the paper because it's going to drop faster than this one. Agreed? If you believe it's because it's heavier that's why it falls. Yes? Okay. But what happens? They fall together. But that has nothing to do with any like crazy glue or anything I put on the book, like, you know. So what's the only difference? What happened? What happened? The book moved the air out of the way so that the air no longer had any impact on the paper. And because of that, the paper was free to fall without air slowing it down. And so you can see they fell together. So it does turn out that on any planet with gravity, all objects will fall at the same rate, regardless of their mass. They will fall at the same rate, as long as there is not an atmosphere, air in our case, to slow it down, right? If there were no air in the room, these would fall together,
and we would die.
and we wouldn't be here to talk about it. But do you understand that? So scientists, I don't know if you ever saw the video of like the men on the moon bouncing around their little things, and they had a feather and they had a hammer. They drop them on the moon and they fall together. Y'all ever seen that video? That was basically the scientists basically going like this to, you know what I'm saying? Because how many times in the past had, I'll say, religion or theology said, you know, Earth is the center of the universe, and then the scientists proved no, it's not, and then, you know, oh, it falls at different rates because of gravity, because of air, and so basically that was just like, look, we told you, we've already proven this. Look, now here it is in your face. Because on the moon there's no air. The gravitational field's not strong enough to hold an atmosphere in. Can't hold it. So there's no air. They showed the demonstration. Well, it's over, right? So if everything on Earth falls at the same rate, if you take air out, then there should be some equation that tells you exactly how far it would have fallen at every point in time, because it's going to be the same for everything, whether I'm dropping a book or a penny or a feather or with no air. with no air, right? Then everything should be the same, yes? I'm going to address the air question in a second because I know everyone's unsatisfied, and as I was as a student, I'm not satisfied with you giving me an equation that only works when there's no air, when there's frickin' air, right? I mean, so, okay, so we'll talk about that in a second. But if that's the case, then they all drop together, yes? And we know that as you drop something, it starts to speed up, doesn't it? So like in the first second, it may have fallen this far. 1 second later, it isn't double that, is it? It's gone even further. And it turns out that it's a squaring relationship, and it turns out to be parabolic. It turns out to be a quadratic function that tells you where things are. And it looks like this. D, let me see, I'm going to give you the one in the notes. I used h of t. Well, all right. There's different versions of this. Okay. H of t equals negative 16 t squared plus v0t plus h0. Now, let's discuss what each of these little things mean. And next to this, I'm going to write down what we are used to seeing when it comes to quadratic functions. This is an expanded form of a quadratic function, right? That's expanded form. So we're used to seeing a number in front of x squared, number in front of x, and a number by itself. A couple of differences in here. First of all, I'm not using f of x, I'm using h of t. So t is the variable? T for time, yes. And then the number in front of x squared is negative 16. Always. Why? What do you think is dictating that number is always going to be negative 16? There's no air. Yes, there's no air, right? So when I let those go, what's the only thing affecting them? Gravity. And that number is dictated by gravity. You move to a different planet, your formula changes. It's no longer negative 16. You go to the moon, it's a smaller number because the gravitational force isn't as strong. If you go to a bigger planet, then it's going to be a bigger number. How many of you who've taken some physics know that the acceleration of gravity is 9.8 meters per second per second? Okay. If you convert 9.8 meters into feet, it's about 16 feet. So it's this formula. Yes, hold on. 32, no, 32. Hold on. We're looking at velocity, which is the derivative of this. It's a Cal 1 thing, don't worry about it. This is dictated by gravity. This is dictated by gravity, all right?
It's called the gravitational constant.
On Earth it is, yes. But I'm saying that number is based upon gravity on the planet you're on. This formula actually works for any planet. That number will change if you're on a different planet.
And it doesn't work for anyone. Oh, the formula is
This number changes. Everything else is the same, all right? Okay. All right, so then what's V, how do we say this? V naught or V sub naught? This is our initial velocity. So let me show you. I'm not going to do the book and the paper because it's too loud. If I just take two markers, initial velocity, if I just let it go, that means your initial velocity was 0 because all you did was just dropped it. If I take the pen and instead, imagine I'm not going to just let it go. I'm actually going to, I'll do it this way. I'm going to give it some initial velocity. That didn't work. All right. Okay, so as soon as I hit it, it went up, right? So it went up and then it came back down. That would have an initial velocity. As soon as I hit it, it leaves and then it starts going up. That velocity, that would be a positive number. If instead I did this, okay, that would be a negative number. Well, think about you shoot a rock, you shoot something up into the air, right? You give it an initial velocity, it goes up, it comes back down. You could be standing on a bridge and shoot something down. This formula will still work. You just got to know how fast the projectile came out of whatever it is you're shooting it out of. Okay? This right here is what?
initial height.
The height. So we're going to say ground level is 0. This is your initial height. Got it? T is time. T is measured in seconds. Everything as far as height is measured in feet in this formula. So we have feet and seconds. You with me? All right, we already know this. If I graph this, This would be a parabola that opens which way? Down. What's the y-intercept? Y-intercept. It's the initial height, isn't it? So with this picture, h0 is here, isn't it? And then as time goes on, I know that this parabola goes down, right? Goes down. So it might do this, right? Or it could possibly, that could have been the highest point, right? Like that, something like that. Just saying this left side of the parabola that extends this way doesn't really make sense to us, does it? Because that's negative time, right? Graphically, we could draw the whole parabola, but the only thing that's really going to make sense to us is the right side of the graph, from 0 on out. You with me? All right. This x-intercept would correspond to what? The time it took to hit the ground, wouldn't it? What would the vertex represent? The highest point. The h and the k mean something here to us now, don't they? The k is actually how high the object went, yes? And the h is how long it took to get to that highest point. With me? Okay. I only have 20 minutes. Example. I forgot about this example. That's cool. All right. I forgot I made this one. We'll turn the lights out. This is actually an example I made. It took me a while to write the code for this one, so that's why I was smiling, because remember how much it took to make this happen. That's a bridge. That's a ball on a bridge. What we're going to do is we're going to throw a ball upward, shoot it up with a little air cannon or something. It's going to leave the cannon little thing on the bridge at a speed of 200 feet per second is how fast it's coming out. As soon as it comes out, gravity starts slowing it down, right? It's going to go up, it's going to come down. This example that I made, it actually is correct in terms of time. If you did this in the real world with no air, this is exactly what would happen. Like if we're timing it right now on our watches, this is how long it would take. It would go up, and it would come down like this. See, it's kind of speeding up. All right, understand what's going on? Okay, now next to it, I'm going to draw a picture of what's happening now. Right? The x-axis is our time axis. The y-axis is how high it's going. See the green part? Doesn't make any sense. Right? The green part is negative time. All right, let's try and do this problem because I only have 20 minutes. Yeah, does that seem too bad? Or yeah. Really? Why? It's this, right? You're going to remember that? Yeah. So just make that a negative 16, a v naught, and h naught, and you're done. All right. Oh, I did not address the air. I did not address the air. I told you I would. I don't want to leave you hanging on that. So why do we not include the air? Here's why. Because if I put the equation up here that takes air into account, it would be too complicated for you to look at in a college algebra class. So what happens, it's kind of like if anyone's taken a physics class, when you first start talking about, like, I'm gonna pull this book across the table, and I'm talking about the forces being applied and things like that. The first time you ever do that, you act like there's no friction. And it makes all the computations very easy. And then later on you add friction in, and then it becomes more complicated. Same thing here. We have a basic function that deals with no air. You want air, it gets more complicated. You want to include the humidity, it gets even more complicated. You want to take all these things into account, right? Because really, if you're like on the top of Mount Everest compared to sea level, even the gravitational field is different there. You want to take that into account? That gets even more complicated, right? So this is just like a general basic formula, good enough for most of the math that you would do, all right? So we're not selling you short, but it's kind of like, it's like, you get a kid who's, look, they're walking first steps. You're like, come on, run a marathon, go, go. Like you can't expect to go from stepping to running a marathon. You can't go, we have to start out basic with basic functions, add the details later, the complexity, and that's what makes physics and stuff get harder and harder and harder. You start adding the things that make it look like the real world. All right, so in my formula, what do I have here? Balls thrown upward from a 200-foot bridge at a speed of 300 feet per second. So what am I given? Initial velocity and an initial height. What was my initial velocity? 300 feet per second. I think I just said it when I was showing you the animation. I think I said 200. I misread the problem. It's 300 feet per second. So that V naught is 300. Why is it positive 300, not negative? It was thrown upward. Okay, if it was thrown downward, that would be a negative 300. And then from a 200-foot bridge, so plus 200. And now I'm going to leave this as a take-home exercise for you to be turned in next class at the beginning of class. I will count it as a bonus on your test. What I want is a detailed graph of this picture. Right? Everything we just did a second ago? Just look at that, you want me to just refer to my own picture? That's it? That's what you want? Yeah, I want you to work it out. So I want you to follow the steps that I did in class. What you're going to run into, which is going to be a problem, is the x-intercepts of this. You will not be able to factor that. So what do you do if you have a quadratic function that you've set, or quadratic equation set equal to 0? What do you do if you can't factor that? Quadratic formula. You're going to need the quadratic formula to solve this. Do you think that's fair? Bonus question? All right. All right, that leaves me about 15 minutes to talk about the exam. So I gave you a review last class. Anybody not get a copy of the review? You need a copy? Let's make sure I've got some spares here. You got a copy?
Yeah, it's online.
Okay. And I've been told that we believe that the answers to these are online. You do? Okay. I'm just trying to see. You don't need to take them out. Do you know what the file is called, or?
It's in the old stuff, and it says like exam review one.
Exam one review solutions. So I think it's probably
exam one review.
SOLN. Okay. Yeah. So the solutions to the review for the exam are online. Is my old exam there too? Did I put exam one there? Well,
I don't know. I didn't put
yeah. So any questions that you want me to address right now, even though the answers are online, anything you want me to talk about off the review? Notice that on numbers 11 and 12, do you need to, no? Okay. On numbers 11 and 12, those are like the new stuff from today. Graphing, I want you to graph a quadratic function that's in standard form, and then number 12 is a ball thrown up with a velocity of 200 feet per second off an 80-foot bridge. So it's just that problem with different numbers. I think the length of this exam, this is about the length. You'll have an hour, 40 minutes. So, you have to come in here like feet hit the ground running, right? You don't want to invest more time into a problem that's going to hurt you later in the exam. Go through the review, understand what it is that you know you're going to get hung up on, and maybe try and either save those for the end or get those out of the way in the beginning. Any other questions? Note card. Okay, I'll do this. I've done this before. I think this is fair. How many of you think you could do it without a note card? Anyone feel like they're good without a note card? Okay, so here's what I'll do. Just for this test, let's not say this is going to be the standard for the whole semester, but since it's the first test, I will allow you to use one sheet of paper, front and back, steps, procedures, formulas, no worked out problems. Nothing worked out. So use like hieroglyphic symbols that only you understand, but don't just work stuff out. All right? That sound fair? Now, if you use that, no penalty. Pardon me? formulas like this. You can have that on there. You can have difference quotient. I won't provide you with anything. So if you have if you don't know the quadratic formula, you better write it down on that. All right? If you do not use a formula sheet, you will have a 5-point bonus on the test for not using a formula sheet. But you have to let me know at the beginning of the test that you're not going to use it, and you have to stick to it. In other words, you can't be like halfway through a test and be like, never mind, I need a formula sheet. You know? So does that sound like a good deal? All right, so 5-point bonus. Just make sure you remind me at the beginning, I'm not using formulas for this test. Make sure you study your homework too. Don't just look at this. I mean, I would start here. If you get through all this, then you should be good. Yes?
Are you doing the binder check?
At the first exam, yes. So you're supposed to bring your binder. I'm just checking for organizational skills. You know, there's that, I don't know, the thing I put on the website where it shows like what I'm going to check. I don't know if I'm going to be real anal about it. If you got a good amount of work in there, I can tell you've been working on, you know, putting stuff in there. We'll be okay. If you have that, you know, do what says you're supposed to, you know, do what it says you're supposed to have. But I'm not, we're trying this out. It's a pilot. It's the first time we've ever required binders in all these 1414 classes. But it's because, like I told you at the beginning, our success rates were like 50%. So we're like trying to intervene and do something that might help. And that seemed like the easiest thing to do is require a binder.
We hold you accountable after doing work, so.
Yeah. So I will reward you if they're good binders. I mean, I'm going to reward you for it. And if it's just a piece of, if it's just one of these with a bunch of stuff in it like this, then that's not going to fly. Because that just shows me you threw everything in there the night before and made sure that you had your version of a binder. So last thing I'll say, when you study for a test, you know, everyone's different, the way they learn, the way that they process things. I've always recommended that what you do is you sit down with a review like this, you turn off the TV, you actually turn your Wi-Fi and your data off on your phone, if you could believe that, like totally disconnecting from the grid, and then give yourself an hour, 40 minutes, and see what you can do. And if you can't do it, circle it, and then once you've established what you can't do, you go back and you review those things and you figure out, you know, okay, that's where you would use your note card. Okay, these I didn't know, I need to write on my note card. If I have to do this, then make sure to remember to do this. I mean, give yourself hints, all right? But don't just be like looking at my solutions. Oh yeah, sure, I could do that. Some of you can. If you're there, that's great. But all right, I have no more for you. Have a great rest of your day. I'll see you on Wednesday. That one? Okay.
So, to finish this one and like the number 12 in
Yes.
the review, we're just going to basically do the steps that we did
Yes.
in class today.
Yep, and really, like, you know it opens down. The vertex, oh, let me turn this off.